The first of the three families we will consider is the conditional model family. So in a conditional model, conditional is a very much abused word. It's one of those words with a million different meanings. So what do we mean by it here? We mean a model for longitudinal or otherwise hierarchical correlated data where an outcome, Yij, subject I, time j, to fix ideas, is modeled conditional on a set of outcomes at other times. And precisely how we select these other times, these other occasions, that remains to be discussed. It could be the previous one in a longitudinal setting. It could be everything else. There are many possibilities. So that is what we mean by a conditional model, one where the relationship between different outcomes from the same people is explicitly modeled by including other outcomes, autoregressive models. Okay, Cox in 1972 introduced the Cox model. But this is not what we're talking about. We're talking about a model introduced by Cox in 1972, way less popular, and that's not difficult because the Cox model is the paper on the Cox model is one of the most cited papers in statistical history. But there we really deal with partial likelihood survival analysis. Here we talk about multivariate binary data. So what Cox did is say, hey, we could call it a multivariate exponential family. If you can do the exponential family for binary data, you can also do it for multivariate binary data, right? So you just have two indices. True. But if you have multivariate binary data, you can look at the individual outcomes. If there is only one, then the n would be equal to 1, and you would be back to the Bernoulli model, to the standard generalized linear model. But if n is greater than 1, you can look at all the pairwise cross products. I should actually circle this. I can look at the 3-way, the 4-way, the 5-way, ... until I have n-way cross products. For 4 repeated measures, I go up to order 4. For 10 repeated measures, I go up to order 10, and you say, yeah, I see that. That's all nice and well. But look at that. How many of those terms are there? 2 to the power n minus 1. So for one outcome, univariate, this is equal to 1, no problem. For n is equal to 2, I have 2 repeated measures. What it then means is I have a main effect, another main effect, and an interaction, 3. And then it becomes 7. And that's a little bit like in a 2 by 2 by 2 table, which I can draw as a cube. And I have something like this, 2 by 2 by 2. Good. Now, I think you start to see coming a major problem. That is, if the n becomes large, I really have many parameters. And here I would like to link back to the toenail data set. I'm really interested in one parameter. That one parameter is the treatment effect, and that treatment effect is written as the evolution difference between two slopes. Slope difference, one parameter. And does this now mean that if I'm using this model, well, with 7 repeated measures, I have 128 minus 1, so 127 parameters a priori. I'm not looking forward to that. So it may not be the best model for the toenail data set, for example, but it could be used somewhere else. Okay, the interpretation of the parameters is quite interesting because I call this a conditional model, but you see me conditioning nowhere on other parameters, on other outcomes, I should say. Well, a small side remark before we go on is here the normalizing constant is written as we call it additively. Here it's written multiplicatively, but the C and the A coefficients transform into each other. Exercise, write down the transformation from C to A and from A to C. Interpretation of the parameters, well, you can work out, and again, you can look it up or do it as an exercise, but that's just for your own interest and confirmation. It's really not necessary to do it. The thing is that the theta ij's can be interpreted as logits. If I look at this thing that I'm circling now, that's a logit, but not an ordinary logit, one that conditions on all the other outcomes to be equal to 0. So we call that the conditional logit of success at time j or at variable j, given that all the other variables for that subject are equal to 0. The odds ratio comes in if we interpret two time points or two observations at the same time. So the pairwise parameters, theta I jk, it's really theta jk, but it's allowed to differ or to vary with subject. But the thing is, I have the pairwise success probability, the pairwise failure probability. So what I've circled now are the so-called concordant probabilities. And what I put a square around, these are the discordant probabilities. But again, I'm looking at two times, j and k. This is conditional on all of the other times equal to 0. So that's why I call it a conditional model, because the parameter interpretation is conditional indeed. There are some advantages, but I have to say, in all fairness, these advantages are predominantly mathematical and not so much data analytic. The parameter vector is not constrained, which means if we all start to throw out parameter values for the thetas, at the end of the day, we will have a valid joint distribution. So it is a rectangular parameter space, which rarely happens for fully marginal model, not even for the multivariate normal, because there are constraints on the parameter space. Really? In a multivariate normal? Yes, because if I have a vector mu, mu can be anything, no constraints. Sigma, though, must be positive definite, and positive definiteness puts a constraint on the parameter space. Not every set of parameters, sigma 1, 1, sigma 1, 2, blah, 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 not every set of parameters produces a valid variance-covariance matrix. Even in the univariate case, it's already clear, because I have mu and sigma square. Well, sigma square should be greater than or equal to 0. It's a silly restriction, you may say, but it is a restriction. So it's not unnatural for it to happen, but the advantage from the model we are considering now is that is not the case. Calculating the probabilities is not so very difficult. You just calculate the functions, you just evaluate this function in every possible combination of the y's, zeros, ones, and there are many, and then you divide by their sum, you get a normalizing constant, and you're fine. The drawbacks are that in many longitudinal contexts where you really are interested in regression relationships, is the probability of success evolving positively or negatively over time? Is it more rapid or more slowly than in the other group? Well, I'm not going to ask the question, given that at all the other times I have a failure. That's not even a meaningful question. So it may not be so easily interpretable. And there is a dependence on the length of the sequence, which we really don't like, etc. So for longitudinal data, the model is less straightforward. Will we not use it? Yeah, we have the NTP data, for example. And next to that, we will also consider other conditional models. If we say, hey, we have so many parameters, could we not simplify it? Yeah, we can do that. We can, for example, throw out all three-way and higher order interactions, and then we get a quadratic exponential model. A bit easier to work with. And moreover, in case you bring it further down to just the linear terms, not even the quadratic terms, it's nothing but logistic regression at each of the outcomes or each of the time points separately. Aha, this means that we are looking at an extension of logistic regression, isn't that so? No, not really. We are not really looking at an extension of logistic regression. We are looking at, yes, it's true, we are looking at an extension of logistic regression, not the extension of logistic regression. And you will see that most models which we consider all somehow coincide with logistic regression when there is no dependence, because the linear case applies in the no dependence case. The theta parameters of higher orders, be it second or higher orders, they capture the association. So in their absence, there is no association, and then we're back to logistic regression. Okay, let's look at the specific version with the NTP data in mind. Well, for practical reasons, we are going to code the outcome as -1 and +1. And that practical reason is very simple. If I code them as 1 and 0, and I say the sum of the y's is equal to 7, you have to know the total. But if I say, if I say the sum of the y's and the sum of the y squares, etc., you basically get only the number of successes. You don't get the number of failures. But if I code it as -1 and +1, and I look at the sum of the y's and the sum of the y squares, I get two different numbers from which I can work out the successes and the failures. That's all. Okay, design. Design is very important, and from design I can actually simplify my model. Hey, dose is applied to the entire cluster, the entire litter, as we say, with these animal experiments. Which means that I cannot distinguish fetuses from the same mother in terms of dose. And are there other ways to distinguish the fetuses? No. So-called exchangeability is useful. That is, the linear predictor is exchangeable. All fetuses from the same mother have the same theta ij. I can just as well say theta I. And I'm going to set the association parameter, which is the pairwise parameter, equal to a constant. By z, I'm going to write the total sum, which in this case is successes minus failures. Then we obtain that the quadratic exponential family model from a few pages ago now reduces to something that awfully looks like logistic regression, except that there is a second term here in the so-called summary statistic z times n minus z. Okay. That's in terms of an example for this conditional model. Let me go to a different type of conditional models, so-called transition models. I mentioned them already before when we were discussing in chapter 17 the relationships between the model families. But here we truly go longitudinal. Measurements are taken repeatedly over time. Now, time is a dimension, a single dimension that flows from past to future at the speed of 24 hours a day. So, if you think about causal relationships, it makes sense to say today is influenced by yesterday, and in turn we will influence tomorrow. So, using previous outcomes as predictors, in other words, is very sensible. The order of the transition model is just the number of previous measures we take into account. That can be 1, 2, or more. But let me give you an example. First, in the continuous case, with a single outcome. So, of course, at the first measurement, that's something we realize now. At the first measurement, there is no previous measurement. So, that one should be modeled a little differently. And from then onwards, for j greater than 1, I have a previous measurement, and I can say, yes, my blood pressure depends on age, gender, dietary habits, etc., but also on the previous blood pressure. Okay. We complete the model by saying the error term at the first time has variance sigma square. At the second time, it has variance sigma square times 1 minus alpha square. You could say, why is that? Well, it actually is something that you don't have to derive if you don't want. It follows kind of naturally from this formulation. The additional alpha here kind of as a variance reducing impact, so that from this formulation you derive that the covariance between two measurements at different times but from the same subject are nothing but a certain power of alpha times the variance sigma square. And that's what we call the AR1 variance covariance structure. In other words, if you have two measurements 0 time units apart at the same time, the covariance is sigma square, the correlation is 1 because it's the measurement correlating with itself. 1 time unit apart, you have alpha times sigma square. 2 time units apart, you have alpha square times sigma square, etc. So alpha is the base AR1 correlation. And if that is 0.5, if we say the AR1 correlation is 0.5, it means two measurements from the same subject, 1 unit apart, have correlation alpha. 2 units apart, they have correlation alpha square, alpha 3, etc. And usually these correlations are positive, and they should then lie between 0 and 1. So the higher powers you take, the closer that correlation goes to 0 until at infinity it completely disappears. Unlike random effects, which induce a random intercept induces compound symmetry, which says every 2 measurements, whether 1 minute apart or a million years apart, they have correlation, constant correlation. In the notation of the linear mixed model part, d divided by d plus sigma squared. Now you may say, correlation going to 0 is unrealistic, but correlation remaining exactly the same throughout history, it's equally unrealistic. So there are models that combine both of these features. The general linear mixed model framework allows for that, so that you have a little bit of correlation that goes away, and a little bit of extra correlation that doesn't go away. We call that then serial correlation, indeed. Huh? Okay, that's all nice and well, but we shouldn't get too carried away by the Gaussian case. We should stay with where we are now, the non-Gaussian case. And what we do is we write, like in every GLM, the outcome as system plus noise, or signal plus noise. Huh? The stochastic component and the systematic component. And we say mu IC is a conditional mean given the history. By that history h, we usually mean everything that has been measured in the past, all the previous outcomes, from the beginning until now, but not including now, because we are modeling the current measurement, and it contains the covariates ever since the beginning up until now. So today's blood pressure is modeled in terms of yesterday's blood pressure, everything before, but then perhaps also in terms of age and gender, etc., or other variables that I measure today, other covariates. So, to generalize, what I do is I formulate a generalized linear model, but in a conditional fashion. That means it's modeled, it's written down, conditional on the history to be known. So a linear predictor could be, for example, the logit of the probability of success is a function of treatment by time interaction, but also of the previous outcome, the previous side effect value, or a function thereof, or a function of the 2 previous values, etc. Now, since you condition on the past, you're actually using the chain rule. You're looking at the first measurement, the second given the first, the third given the second, or more generally, the third given the second and the first, the fourth giving 1, 2, 3, the fifth giving 1, 2, 3, 4, etc. It is the law of total probability, which means this is a product of independent contributions, which drastically simplifies the likelihood. Usually, it takes the form of a logistic regression that you fit cleverly. So every data point, conditional on its past, can be considered independent. It's not an assumption. That's actually the law of total probability. It always applies. In a linear mixed model, we cannot do that because we say we model the sequence conditional on random effects, but these random effects don't make the sequence further independent. It explains a good amount of the variability, but it might also leave in some of the variability. Don't forget that actually in the base model that you have introduced, you do assume that the random effects make the measurements further independent, and that's then called the conditional independence model. Okay, a logistic regression example is, there we go, autoregressive of the first order. Stationary autoregressive of the first order. Why autoregressive? Because you model an outcome given the past. First order, because the past is restricted to the just one preceding value. And stationary, because you have the constant alpha and nothing else, just a constant alpha. Okay. So, the thing is that in the Gaussian case, you can easily derive from a conditional formulation, the marginal one, not now. You do have recursive formulas. But just imagine that all these functions are e to the power divided by 1 plus e to the power. how on earth are you ever going to simplify that? So these recursive formulas don't lean themselves very naturally to simplification. It doesn't stop us from applying it in practice. We don't need these marginal functions. We can say, okay, let's formulate a first transition model in the toenail data set. So treatment, time, treatment by time interaction, and then a dependence on the previous outcome. But then we say, hey, wait a minute, it is a balanced data set, but we have measurements at 0, 1, 2, 3, 6, 9, 12. They are unequally spaced. So shouldn't we take that into account and say, maybe the autoregressive parameter is different in the first part of the study relative to the second part of the study. So we can do that, for example, by saying we have an additional excess parameter that we add, alpha 1 plus alpha 1a, and alpha 1a only plays in the first quarter when the measurements are more equally spaced. Or we could look at two prior occasions, and that's then a second order autoregressive model. So here are the three models summarized. The first model has a dependence on the previous one, and guess what? The dependence on the previous one is significant. We have that autoregressive feature. We have, in other words, correlation between the repeated measures. But we also see, if we split this in an earlier versus a later dependence, that the 448 is a compromise, because the late dependence is 359, smaller. That's this. But the early dependence is the sum of the two. It's 359 plus 1.56. So that model, likelihood ratios confirm that is a genuine improvement. We do have a significant difference in the autoregressive phenomenon in the first quarter relative to later in time. So it's actually not first order stationary, it's first order non-stationary, because we have a jump. And second order, there we see that adding a second order to model 1 doesn't contribute anything. Well, could you consider a second order version of this one? Oh yes, you could also do that, but also take the difference in lag into account. You can go one step further and say, hey, wait, what we are actually doing here is we have a treatment effect, a time effect, and a treatment by time interaction, with, incidentally, this being our main parameter. But what all these models do is they don't touch those in terms of the dependence on previous outcomes. In essence, we add a constant if the previous measurement is a 1, and we don't add a constant if the previous measurement is a 0. So in other words, we basically have a model with two intercepts. The intercept is minus 3.14 when you start from a 0. The intercept is minus 3.14 plus 4.48 when you start from a 1. You can say, okay, but maybe also the treatment effect is dependent on the previous outcome, and so is the time effect and the treatment by time interaction. Well, you can do that by point blank saying, I have my 4 regression parameters. If I come from a 0, and I have 4 other regression parameters if I come out of the previous time point with a 1. Much more difficult to interpret, but you do see that the treatment effect, so it's like the treatment effect now, at this point, given that I come out of a failure, or given that I come out of a success. In other words, I can rephrase it and say, what is the probability of a severe infection given that I had a severe infection? And what is the probability of a severe infection given that I had no severe infection at the previous time? Of course, they are going to be different. And that's something that you see in some parameters, but not in all. So, transition models in SAS. What I need to do is just include the previous outcome as a covariate. It's just another covariate, and then I can use logistic regression. The only thing is that the previous outcome, if, for example, I have a data set with subject 1 with 4 measurements, and then I have time 1, 2, 3, 4. If I'm at time 2, and I have an outcome yi2, well, or patient Y1, 2, patient 1, 1. If I want to use this measurement as a predictor, I need to have it on the same line. So what this macro does, we also use it in the context of dropout modeling, so that's why it's called dropout, is it actually makes the previous measurement descend one line so that we can use it as a covariate. And if we are going to use a second order, we have to take the previous, so we have to apply this twice. That's all. Okay, so this is what it's going to look like for the first subject, as I was informally indicating. Huh? So, for example, you see the previous outcome, which is this entire sequence, but then coming down one level. And then you bring it down another level to go to the previous outcome, etc. And then the only thing you need to do is fit this logistic regression with the previous included, for example. When both predecessors are used, you have to add that additional variable here in the model. So you're going to, because now we only have previous one, we have to have also previous two added to the model. And if you're going to have that additional variable 1a, because you say earlier in the sequence and later in the sequence, it's a different story. The association is stronger earlier on because the measurements are more finely spaced. Well, then you define the previous outcome A as the previous outcome, but you set it equal to 0 for later in the sequence. So you let that one contribute early in the sequence, allowing it to increase, or if that would be the case, but I don't think so, decrease the autoregressive effect. Otherwise, it's only the parameter 1 that plays a role. Okay. That concludes the conditional models, and still within this part, but in the next chapter, we will start talking about the marginal models.